Yeah, can you guys see my screen now? Okay, let me start with some public key cryptography. Let's go. So after you learn the Triple M chapter 3, you have pretty good foundation for learning public key cryptography, you know. So I think it's pretty nice opportunity to include it here. The main reference for this talk is Introduction to Mathematical Cryptography, the book, also the cryptography course by Dan Bonet. Okay, so credit go to them. So first, we are going to review some mathematical background, some pretty important concepts. Zima MZ, which is the set of from z to m minus 1, right? It is the ring of integers modulo m. You can do two binary operations in a ring, which is addition and multiplication. So they are denoted as nothing. So for the notation, usually I prefer z mod mz, right? But some people just write zm, so they are exactly the same. So this notation, mathematically, it is the quotient ring of Z by a principal ideal MZ. But what does it mean? It doesn't matter. You will learn more about that in chapter 4. Wait, I can't hear anything. Wait, can you just type in the... Wow. Sorry about that. Oh, I thought it's a question. No? Okay, let me continue. So, for example, Z mod MZ, an example is when the M is 5, you have Z mod 5Z, right? So it only has 5 elements, which is 0, 1, 2, 3, and 4. And you can do addition and multiplication here, both in mod 5, right? So a corresponding concept is the unit group, which is just adding a star on here. So sigma mz star means you pick all the co-prime elements with the modulus. So GCD AM equals 1. So these are the elements that have modular inverse in sigma mz. So the elements here are called units, and this group is called the unit group. Right? For example, sigma 24z, you have 24 elements from z to 23. For the unit group, you just have a few elements. These are the elements that have modular inverse, right? So 24 case is a composite, so not all elements have inverse. But for Zima PZ, in particular Zima 7Z case, every element other than 0 has an inverse. So the Zima 7Z unit group is all the elements from 1 to 6. You can see the number of element is like p minus 1, where p equals 0. P equals 7. So this is like a special case, which is very important to understand, right? Zima PZ case. Moving on, the Zima PZ is also denoted as FP, which is a finite field. This is a theorem you have to prove, but I will omit that. Zima PZ star is also denoted as FP star, right? So this notation, they are the same. They are the same, and they are the same. Okay. Do we have questions so far? No questions. I'm going to continue. Okay. So a super important theorem is Fermat theorem. You will see that a lot in cryptography. The theorem says that P be a prime. So pick any element from the unit group of Z mod PZ. You will have this x to the P minus 1 equals 1 mod P, right? This is a way to compute any element from the unit group to the P minus 1 power, right? So for example, when P equals 5, you have 3 to the 4th equals 81, which is mod 5, it becomes 1, right? So this formula holds for every element in the unit group. Okay? So for the application of Fermat theorem, you have many applications, but I'm going to talk about 2 of them. So for first one is you actually can compute modular inverse with Fermat theorem. How is it done is you take the statement from the formula, then factor x out, right? You factor 1x out, and then multiply x inverse on both sides. X inverse exists because every element in mod P has inverse other than 0, right? So in the end, you will have a formula for computing modular inverse in mod P. So this is a formula. You can do that, but it's less efficient than Euclidean algorithm. So in general case, extended Euclidean algorithm works for all numbers. So for Fermat theorem, you can only do the mod P case, not mod n in general, where n might be a composite. So the other application of Fermat theorem is you can generate a prime. This is not recommended, but theoretically you can do it. So how it works is, for example, you want to generate a random P. For example, in RSA, the length is 1024. Your goal is to generate a large random prime. First, you pick any integer, not necessarily a prime, just a random integer from this interval, 2 to the 1024 and 1025 minus 1. You take any integer from the interval, you try a Fermat theorem on it with base 2 to the P minus 1 power. If the result is 1 mod P, you know that P is a prime. Otherwise, you just repeat. Actually, there's a subtle thing here is Fermat theorem never says the only, you never know the P is actually a prime, but with high probability that it is prime. So there's a theorem you can prove is getting a false positive, the probability is negligible, so you can the algorithm is trustworthy, but not 100%, you know. But the probability of getting P is a composite this way is super small, so we can ignore the fading case, you know. Let me see the questions. Yes, Fermat theorem has many applications. I'm just like randomly pick some. Yeah. Yeah, I'm sure it works for exponentiation. Yeah. Okay, so moving on. Let's discuss the structure of the unit group, but in the mod P case. So there's a theorem by Euler saying the unit group mod P is a cyclic group. So what is a cyclic group? It means there is a generator in the set which generates everything. So the identity element 1 is just g to the p minus 1. Therefore, in the set, we don't include this element because 1 and g to p minus 1, they are equivalent, right? So the Z mod PZ unit group contains elements of 1, generator, multiply, generator, you know, just keep multiply g until you reach to this, and then you multiply G one more time, you go back to 1. This is like cyclic group. You can visualize as like a clock, you know. So you just go one circle and then another circle. They just repeat themselves. Right? So G is called the generator of the unit group. For example, take P equals to 7 case. 3 is the generator because you can compute 3 to 1, 3 to 2, 3 to 3, everything. It covers everything in the group. So there are ZMOD 7Z has 7 elements. ZMOD 7Z unit group contains P minus 1 element, right? So 6 elements. Using 3 as a generator, it covers everything. So they are all distinct, right? So 3 is a generator, but it doesn't mean every element is a generator. For example, if we take 2, we can see if we take G equals 2, then the thing just repeat themselves. So 1 to 4, 1 to 4. It only covers 1 to 4. It doesn't cover the other elements. So 2 is not a generator. Okay. And moving on, a very important application of the elementary number theory we learn is Euler phi function. So this is using RSA heavily, right? So I'm going to introduce it here. What is the phi function? Phi function is the number of elements in the ZMOD and Z unit group. So this thing is pronounced like the number of. So the number of elements in this unit group is equal to, they are the same, right? Just the number in this set. The set contains all the elements that have co-prime elements, right? So for example, we can compute phi of 24 equals 8. I think we did it somewhere above, okay? I think here, right? There are 8 elements. So phi of this unit group is 8. You can see 8 elements here. For the ZMOD 7Z case, you will have phi p equals p minus 1. This is pretty important. This is using RSA, right? Because every element has an inverse. So every element has a coprime property. So this holds in general. Some computational discussion. So how to compute more complicated phi? If the number is p to the a, where p is a prime, you have this formula. Okay, so you can factor p to the a out, and it becomes like this. This is super easy to compute, right? You also have the I don't know what it's called. Feels I think it's called some linear property, you know. So phi of a times b equals phi a times phi b. Oh, it's like bilinear pairing. Okay, so for example, if we take a is a prime, b is a prime, so we have phi p times q equals to p minus 1 times q minus 1. Yeah, that one is using RSA, right? So for a more general case, by fundamental theorem of arithmetic, you can factor any integer into a like the product of prime powers. Okay, so this the theorem implies you can factor everything. So let's do some simple algebra and factor p1 to the u1 out, and then you just factor this out, and move everything to the left. Then this thing computes to n, right? So in the end, this is like a general formula for computing phi n when n is any positive integer. So there's also a important theorem by Euler saying pick any element from the unit group, then x to the phi n power equals 1 mod n. You can try that with a few examples. This is always true. Okay, so that's the end for this subsection. Do we have any question?
What's the name of phi?
What's the name of phi? The name of phi is
Yeah.
phi. This is
No, I
called the phi
mean,
function. Oh, or it's called like the totient function. I just call it
yes.
phi function. Yeah. I think in textbook, yeah, something like phi function. Yeah. Yeah, the name of phi is just phi. Okay. No questions so far, so let's move on to Diffie-Hellman. So this is a pretty short introduction, okay? So in traditional symmetric cryptography, you will have a secret key. So Alice and Bob, they will be using the same secret key. So the question is, for example, Alice and Bob are two people on the internet. They don't have a reliable way of exchanging the key, So they have to keep the secret key secret. So before Diffie-Hellman, you will have like a third party to do that, You have to give the key to the trusted third party, and then they distribute the key to Alice and Bob. But Diffie-Hellman solved a problem that you don't have to rely on a third party. You can just let Alice and Bob communicate with each other, and following this algorithm, they can exchange a key on the internet, which is a like insecure channel, right? So in the key generation phase, there says you still have like a third party publishing a large P and like a generator G. So this phase you can think of as a like a government agency. They post like a standard, you follow the standard, you have to trust the standard. It has no backdoor. So the keygen phase is like you follow the standard, and then this G is having a large prime order in the unit group of the ZMAP PZ field, so that they can just brute force it, right? You have to have a large prime order. So once you decide what P and G is, Alice and Bob simultaneously, Alice pick a secret A. So this is the secret key of Alice. This is probably I shouldn't call it secret key, it's just like a secret large integer, I think, right? So Alice compute capital A equals G to the A mod P. Bob computes B equals to G to the P mod P. So there is some kind of symmetry going on, They are just like using the same formula, and then over the internet, Alice sent A to Bob and Bob sent B to Alice. They exchange the encrypted thing, and then Alice can compute B to the A mod P. Bob computes A to the B mod P. So another symmetry. So we claim that in the end they have a same shared secret. So this number is the same as this number. How to prove it? Super easy. Take from capital B to the A. So capital B is G to the bit power, G to the B to the A. And because A and B are just integers, they are commutative. You can swap the order and then go back. So you prove they are the same. So in the end, Alice and Bob will have the same shared secret using a simple algorithm. Any question with that? Oh no, I'm not going to talk about the broadcast attack. Yeah, that one is, yeah, that will take too much time. Yeah, I would probably go like more 20 minutes more maximum. Yeah. Yeah, but if you guys interested in that, I can cover in the next session maybe. So the security of Diffie-Hellman, there's a problem named Diffie-Hellman problem, DLP. Oh, not, oh, wait, not DLP, DHP. DLP is a discrete log problem. So let P be a prime and G be an integer. This Diffie-Hellman problem is just a formalization of the protocol we just talked about, right? So for like eavesdropper Eve, she cannot compute G to the AB power based on capital A and capital B. Yeah, because over like an internet, Eve can just capture the communication between Alice and Bob, right? So Eve knows A and B, which is G to the A, G to the B. She knows these two equations, but she has to solve the discrete log problem in order to recover either A or B to compute the final shared secret, which is G to the AB power, right? So the challenge for Eve is she has to solve the discrete log problem. So this is a passive attack scenario, right? So in a passive attack, you can assume Diffie-Hellman is secure, but in like active attack, for example, so this guy will be named like Mallory, right? So Mallory will be the man in the middle and intercept this communication and provide some fake exponent here, So and manipulate the protocol. Diffie-Hellman is vulnerable to man in the middle attack. Yeah, but that's another story. We are not going to investigate that today. Okay, so any question about that? No questions, maybe. Okay. So no questions on Diffie-Hellman, right? We all understand everything, right? Let's move on to RSA then. Ah, wow, this one is pretty long. Okay, so a little bit background. Recall that we just talked about Fermat-Little theorem. It says for any prime p, you have this a to the p minus 1 power equals 1 mod p. Of course, this case only holds for the case that p does not divide a, because if p divides a, you will have a equals to 0 for everything, and a raised to any power is still, I mean 0 here, 0, 0, 0, 0. Yeah, 0 here. So Fermat-Little theorem is only for prime p, modulo p case. So that's so is the theorem true for non-prime m, so composite m case? So in general, the answer is no. But for learning RSA, we can generalize the Fermat-Little theorem to the case where m equals p times q, where they are two distinct prime. And so without proving the theorem, first we can just go over two examples. One example is, no, I mean just one example here. So for example, m equals 15, 15 equals 3 times 5, so p equals 3 and q equals 5. In such case, you can try that a to raised to the 4th power. So about like half of the elements satisfy this equation. So the other half satisfy this equation. And you can see like a pattern here is when the GCD of A and 15 equals 1, so they are all co-prime, you will have something similar to Fermat theorem, but not the others. Yeah, you can kind of tell the pattern here. So the idea behind this is just you can say basically this equation is equivalent of saying 15 divides a to the fourth minus 1. Okay, so they are kind of equivalent. And you can look at the decompositions where mod 3 and mod 5 case. You can translate the mod 3 case into 3 divides a to the fourth minus 1. And this is 5 divides a to the fourth minus 1. If we can prove that they are true, then combining these two information, we can say 15 divides a to the fourth minus 1, which is equivalent saying this equation is true, right? So you can verify that a little bit. So for the equation 1, the mod 3 case, you can use Fermat theorem to say a to the fourth is a square, then square again. And inside the parentheses, we have a p minus 1 power. And by Fermat, this is 1. The other equation is easier to prove. This is just a to the p minus 1 power. So you can use like Fermat theorem twice to prove the decompositions are true, and then the original statement is true, right? So this is the idea. Yeah, this is true if you can prove that the thing is a multiple of p minus 1 for one decomposition and then the other, right? So you can combine the information and prove the original statement. So in general, you will have this big Euler formula for P times Q. So basically, yeah, just this equation. P and Q are distinct prime just in RSA, and G satisfy a certain condition, and then you can have something similar to a Fermat proof. It is like a generalization, but is only for the P times Q case. Fermat theorem is not true for general composite N, So yeah, this one is a nice thing to know. It will be used in the RSA proofs, but yeah, it's not super important. If you don't understand it, you can just skip it. Right? So any questions so far? Wow, what are you guys talking? Wow, RSA meme. Oh my God, what is this? Anyway, I'm going to continue. So the security of RSA relies on solving the congruence x raised to the 8th power equals the ciphertext mod n, where n is p times q. Right? So there is a misconception that people always say, oh, the difficulty of RSA relies on the factorization of integer. That's partially true. So because if you factor n into p and q, you can compute the Euler phi thing. You can break RSA easily, but in the original statement, x to the e is the encrypted message. So this is the expression for the encrypted message, which is the ciphertext. Okay, so Eve's job is to compute the e square root. Yeah, because we are solving for x right now. So the main task of the attacker is to recover x. It's not factor n, although factoring n can help breaking the system. Okay. So there are a few things to talk about. First, if n is a prime, it is pretty easy to recover x. So basically the proposition is this one. Wait, hold on. Okay, so this proposition is a formalized version of this statement. So you cannot have n equals to a prime. Okay, so yeah, if n is a prime, it is super easy to compute the inverse. And yeah, let's say like, for example, just let this p equals n, and then you will have d times e equals 1 mod n minus 1, because you already know n. So n is like a public information you can get from the internet, so you can easily compute this modulus and then do the modular inverse computation, and then you recover this d, which is the decryption component in RSA, right? So first thing, n cannot be prime. So n must be the product of two large primes, p times q. So yeah, I'm saying here that if the attacker can factor the modulus, then it's super trivial to break RSA, because once I know p and q, I can compute the phi function, the phi n equals p minus 1 times q minus 1 we just proved, right? So after that, I got the phi information. I can come here and say, oh, so this is phi n. So I can just compute the modular inverse. This is super fast, right? I can compute for D, which is the decryption information, and I can do that on C, which is the ciphertext. So the idea is, once I factor in, it is super trivial to recover the message, right? So this proposition is just a formalization of the statement here. So don't worry about it. So this one kind of proves the correctness of RSA, because you have to prove that when you recover D, you have to have a unique solution. Otherwise, it becomes like a non-deterministic algorithm, right? So for encryption, we want to like decrypt one ciphertext to one plain text. We cannot have multiple solutions. So this proposition proves that it has a unique solution. So we know that one ciphertext correspond to one plain text, right? So here is the actual protocol of RSA. Okay, let's go through that. Alice and Bob talking to each other. First, Bob choose a secret primes. They must be large primes p and q. Okay, so also Bob picks a encryption exponent e, which satisfy this condition. Why is that? It doesn't matter. It has something to do with this proposition, right? So it has to pick a special E. Then Bob publishes the public key pair NE on the internet. So N is the product of the large primes P and Q. They must be random also, right? Random primes. N equals P times Q, and also E, this is the public key. So this goes on the internet. The security of this is relies on the factorization hardness, right? So once I publish this on the internet, I assume attacker cannot factor my N in polynomial time, right? So they are secure. Also, E has nothing to do with the decryption, so I can safely publish that on the internet, right? So after that, Alice, we go into the encryption phase. Alice picks a plain text M, so this is the secret message she wants to send to Bob. So what Alice does is she uses a Bob's public key pair, which is N and E. I compute a ciphertext. Super simple. It just reads the message to the eth power, and I do that in modulo n. So n and e, they are information provided by Bob's public key. So I just use his public key and compute my ciphertext. Okay. So after that, I send the ciphertext back to Bob. So this is the encrypted message. I send it to Bob. Okay. So when I send this ciphertext on the internet, it can be seen by anyone. So, for example, attacker Eve, she can capture the ciphertext, but this is pretty secure because she has to compute the eth root of this congruence. And we assume this is hard because we don't have a like efficient algorithm for computing the eth root, right? So when Bob sends this public key to Alice, he assumes the hardness of integer factorization. So this information, he assumes this information is secure. Okay, so when Alice sends the ciphertext back to Bob, she assumes attacker cannot do like taking the eth root from this congruence. Okay, so that's two hardness assumption here. Okay. So in the end, Bob receives the ciphertext. He can compute D, which is related to the E is the encryption thing, right? So he can compute that. Why? Because Bob has information about P and Q. So this one is like a trapdoor function. So what is trapdoor function? It means when I have a certain information, I can compute the function. But without that information, it is impossible to compute it, right? So the reason why Bob can compute the decryption exponent D is he has information about P and Q. If any attacker wants to compute the same thing, attacker has to do the factorization, which is assumed to be hard, right? So in the end, I can compute I'm prime, which is I raise the ciphertext to dth power and do that in mod n. The recovered message should be the same as the original message because it is proved in this proposition. Okay. So do we have questions so far? Wow. Oh, I see the question saying if we pick 3 primes, then compute n. I think it's not safe because, for example, you have more primes. That means each prime component is smaller, right? So it is easier to factor everything. That's what I'm thinking. So for example, there's a famous CTF challenge saying. For example, we have n equals like the product of 10 primes. Then you can just go on FactorDB, like the factor database, and look look up that, right? Yeah, because n is fixed. If you have more component making up that n, then each component is smaller. Okay. So this is the last part of this talk. Wow, we are hour and 20 minutes already. Okay, let's go over this fast. So the security analysis, I just covered that actually. So the setup is PQ are 2 random large primes. N is the product of them, and E is the encryption, the exponent, and C is the ciphertext, and they are represented in integers. Okay. So the problem is I have to solve the congruence x to the eth power equals the ciphertext mod n. I need to recover x. So, oh wait, hold on. Okay, so recall that in the Diffie-Hellman problem, we were assuming that the discrete log problem was hard. So you can see kind of a symmetry here, we are dealing with congruences in both Diffie-Hellman and RSA, but in Diffie-Hellman we worry about the exponent. In the RSA, the exponent e is actually public. We only worry about the base number, which is the message x, right? So yeah, it's kind of fun here to see like a symmetry between two protocols. So in RSA case, we assume taking the eth root of this congruence is hard. That's the security assumption. I just talked about this. So if Bob knows P and Q, which he does, he can easily solve for X. So this is the trapdoor function I just talked about, right? So without this trapdoor function, so for any other people, for example, attacker called Eve, she does not know P and Q, so she cannot solve for X. This is the trapdoor function difficulty, the assumption made by the RSA crypto system. So if you can break that assumption, RSA system is broken. Okay. And have a little bit more discussion on the RSA. The first one is the choice of E. So it is obvious that when E equals 1, ciphertext equals plaintext. So this one has no encryption at all. You can just take that ciphertext. It is actually in plaintext format. Okay, so E equals 1 does not work. How about E equals 2? In that case, the GCD of E and phi n is not 1. So here we are making a condition that saying when you pick E, you have to satisfy the E has to be coprime to phi n, right? So E equals 2 does not work. How about E equals 3? It works. In fact, I think E equals 3 case is pretty secure, but some people will argue that although they cannot come up with like an algorithm to tag the E equals 3 case, So this one is pretty secure, but it's not commonly used. So what is commonly used is E equals to 65537. So this one is commonly used. This is the gold standard of RSA, And so if you are building like a lib, you want to follow this standard. So just pick this E, okay? And the second remark is if Eve knows P plus Q, she can break RSA. So why? We can see that the objective of Eve is computing this decryption exponent D, right? So the formula for D is this. So this is phi n. DE equals 1 mod phi n. We can expand that formula a little bit. You can see it is P times Q minus P minus Q. Then you group them together is minus parentheses P plus Q. P times Q is just N. This is a public knowledge. You have that, right? So if you know the answer of P plus Q, it is equivalent to breaking the RSA system. Okay. And also here's a fun proof that I claim that knowing P plus Q is equivalent to knowing P and Q. Why is that? Because consider you take a polynomial with some x. This x is just a variable, okay? So x squared minus P plus Q parentheses times x plus PQ. So you can use that famous quadratic formula to compute that there are two roots of this polynomial. Okay, so yeah, you can see P equals to this and Q equals to this, or just swap the order. It actually doesn't matter. Okay, you can see from the expression that P plus Q, if you know the information of P plus Q, this N is public knowledge, so you can solve for P and Q fairly quickly. Okay. Yeah, this is just a fun proof that saying the equivalence of P plus Q and PNQ, but you don't have to do that because once you know P plus Q, you can just compute this phi n, this. Okay. So the last thing for today, I think I just talked about this. Yeah, this one is saying the difficulty of RSA is taking the eth root is not factoring n, although factoring n can break the system as well, right? So an attacker Eve, if she can take eth root, she can recover this x directly without computing p or q, right? So that's saying if I can compute the eth root of this congruence, even though I have no knowledge about P and Q, I can break the system. So if some people just claim like the security of RSA depends on integer factorization, that's not 100% correct. Okay, so this is what I see on the internet, right? I capture this message, this encrypted message. If I can take its root, I can just recover a message without computing P and Q. Okay. Okay, so that's all for today. Wow, that was a pretty long session. Okay, so for future research, I'm sharing this number theory note from Stanford Applied Crypto Group. Also, I learned many attacks from Dan Bunet's paper. Okay, there's a survey paper talking about all types of attacks. And unless if you are interested in RSA attacks, you can go to Crypto Hack. I encourage you to solve all the questions there. Okay, so pretty high quality CTF challenges. Okay. Wow, that was a long session. We finished. ECC invalid curve attack. Wow, that was long. That was long. Oh my God. You are welcome. I would like to present this. Wait. Let me read this question. No, so ECC invalid curve attack is not like the well-known signature malleability attack. No, the idea is if the attacker, no, I mean if the code does not verify the points sent by user are actually on the curve. So you know that in elliptic curve you have to verify the thing. For example, the user sent you a point, you have to check that the point actually satisfies the Weierstrass equation. Yeah, otherwise Alice can send you some fake points that lies on other curves, right? So if she decides to do that, she can send you some points from like small subgroups. She can repeat that process for example, for n equals 2, n equals 3, n equals 5, n equals 7 for all the primes. Recall that in Chinese remainder theorem, we say if I know a list of congruences in that form, all the modulus are co-prime, then I can solve for a solution in the large modulus, which is the product of everything. So invalid curve attack, the idea is just I collect a system of congruences, and then each modulus pair is co-prime, and then in the end I can solve for the answer. So the idea is if I repeat that process for large enough times, I can get a huge list of congruences, right? So the product of all the modulus, they become a huge capital N. So my solution, so the solution is the server's private key. The private key compared to the large modulus, it is actually small. So I want to make sure that the private key is smaller than the modulus. So when I solve for Chinese remainder theorem, the secret key is just that key, you know. Yeah, do you understand that? It's like, so my modulus is large, my private key is relatively small. So when I solve for that congruence, my solution only lies in the first circle. So without the plus k, the plus kn part, you know. So that's the idea of the invalid curve attack. Yeah, Dan Bonnet is a legend. Yes.
I have a question about your final remark of the answer. You said
Wait. I can't hear anyone clearly. Please just leave your question in the comment. Yeah, I think I'm
okay.
having some internet issue. Next time I'm going to let someone else record a video. Yeah, today is like messed up. Wow, I'm not legend. Far away from that. But I'm becoming a legend in the future. So people complain about the Bonnet's course is too theoretical. I don't think so, actually. I think it's pretty applied already because I have taken more theoretical cryptography class. Yeah. So you can Google that, for example, something like the MIT cryptography class taught by Goldwasser. That one is more theoretical. Yeah. So yeah, Dan Bonnet's course is super helpful. I encourage it, like I recommend you to do it like right now. Yeah. Yeah, that one is a must. Also probably the book called A Mathematical Introduction to an introduction to mathematical cryptography. That's my main reference. Okay. Okay, I see question saying if Eve can solve for the congruence, would that mean Eve can break the DL problem? No. No, they are different. Think about this. So in RSA, we are solving for x. Okay, we are solving for the base number x. We are not solving for E because E is already public. Okay, so in RSA, the hard problem is you can't compute the ETH root. Yeah, I will just type in the comment. So in RSA, the hardness is you cannot compute ETH square ETH square root. In Diffie-Hellman is you cannot solve for the exponent. G to A mod P. Yeah, so they are distinct problems. Even though you can solve the RSA problem, doesn't mean you can solve Diffie-Hellman problem. What's the name of the problem? I think in RSA it's called the problem is the modular nth root. In Diffie-Hellman, it is just discrete log. Yeah. Yeah, solving crypto hack challenges are pretty time consuming, so yeah, I never have time for that. Okay, so seems like we don't have more questions. How about we call it a day and see you guys next week? Yes, I'm going to share the notes. Yes. I'm going to upload it to my GitHub and share the links. Yes, of course. Okay, I will see you guys next week.